Kernel with his latest kernel report. So welcome John Corbet of Linux with Attendees.
All right, thanks, Jim. Thanks. Is that okay? Thanks, Jim. Thanks, everybody, for being here. Got a lot to cover. We're going to go fairly fast. Hopefully, I won't leave people behind. I will start, as is my wont, by looking at the recent history, how we got to where we are now, and sort of where we are. So this is a version of a table that I have been putting up for a while yet. This is a set of recent kernel releases over the course of the last year, since the 3.13 kernel was released in January of last year. You can see there have been 6 releases coming out roughly every 2 months. They're all big releases. Each one had at least 11,000 change sets in it, often usually more than 12,000. And in the case of 3.15, actually almost 14,000 change sets that went into there. That was the biggest kernel release that we have ever had in history so far. I assume that we will manage to surpass that again. Traditionally, I put up a lot of statistics about where the code is coming from, the company supporting it and all that. I've actually taken a lot of that out of the talk this time around. But if you're interested in that stuff, you're in luck, because as Jim mentioned this morning, there's a report that just came out of the Linux Foundation where we pulled all that information together and put it down in lots of nice tables and stuff. So all the information is there. I recommend that if you're interested in that kind of information, you take a look at that report, because it covers it in way more depth than I could do here. But I will look at a couple of things here. As I noticed, 3.15 was our biggest kernel release ever. But if you look at the trend over time, you can see a pretty obvious trend there, even without me superimposing a line on top of it. This plot here is looking at the entire Git release history. So starting back at 2.6.12, almost exactly, I'm getting close to 10 years ago now. So that's 10 years worth of kernel history. And you see that the amount of change, the rate of change going into the kernel is just going up over time. This seems to be a pretty unrelenting trend. I don't see it changing anytime soon, even though there was one time a reasonably well-known kernel developer named Andrew Morton said that he thought the rate of change would slow down a bit because we had to actually finish this thing sometime. He actually said that. He said that here. So he doesn't say that anymore. So anyway, the rate of change continues to go up. If you think back, actually go back to that slide just for a moment there. The other column there over there is the number of developers participating in each release, which you see is also steadily going up over time, to where we now have over 1,400 developers participating in every single kernel development cycle. So if you think about that trend, you think about the amount of change going up as well, and you would think that the process has to be slowing down at some point, because we've got more and more change going in. We have more developers to try to coordinate and make work together to integrate all of this stuff. Things would have to bog down at some point. But the actual trend looks like this. The amount of time it takes us to create a kernel is actually dropping over time. It started at something well over 80 days some years ago, and is now down to an average of about 66 days to produce a kernel. The last 3 kernel releases have all come out in exactly 63 days. We seem to have settled into that pretty well. I believe that the next one, be it called 3.20 or 4.0, will take no longer than that. So I don't know how much shorter we can get. If you extrapolate that line, we get to 0-length kernel development cycles in the 2020s somewhere. I don't think that's going to happen. I don't think it's going to get a whole lot shorter, just because you need a certain amount of time to test things just to find the problems and so on. But I thought that a while back, and it continues to get faster, so who knows? What I've been talking about, of course, is the series of mainline releases produced by Linus, but that's not the kernel that most of us run. Most of us run something based on the Sable series, generally run by Greg Kroh-Hartman and various other people who also participate in this. These are the 2 kernels that are currently under long-term maintenance by Greg. And if you look at it, you see that, in fact, there have been a lot of changes made to these kernels after Linus releases them. So 3.10, which has been in stable maintenance for about 1.5 years now, has had 68 updates with over 4,000 fixes applied to it. And 3.14, which of course is a newer kernel, has had 2,700 some fixes applied to it. And so you might be wondering, well, what kind of kernels are they that we're putting out that need that many fixes applied to them? And the answer to this really is that it's not as bad as it seems. What happens here is that a lot of people will not actually run a new kernel until it has come out as a stable kernel release. And a lot of the problems that come up with kernels are tied to specific hardware or specific workloads or both. So there's just no way that we can find these problems until the people who are actually going to be bitten by them run the kernel and are duly bitten. So there's always going to be a fair amount of stuff that comes in after the kernel release, because that's just the nature of kernel development. There's no way that we can test for these problems on our own. As it is, most of these fixes are pretty small. Some of them are actually just minor hardware enablement things that aren't actually fixes and all that. As far as I can tell, most people are pretty happy with the quality of the kernels that are coming out. And by the time you apply this stuff to it, which happens fairly quickly, you have a pretty solid base upon which we are all building the whole Linux-based ecosystem that we're well familiar with. So what have we done over the course of this last year? I can't possibly list everything. I could fill a whole talk with that and still not list everything. But we can highlight a few things. We've added 7 new system calls to the kernel over the course of 1 year. Each system call, of course, is a new entry into the kernel. It's a new functionality that we have not provided before. So we're adding some interesting new functionalities here. I'm going to come back to a few of these system calls later in the talk and what they do. On top of that, we've added some pretty major features, such as deadline scheduling, which is a development that was underway for years outside of the mainline kernel. Deadline scheduling is of interest primarily to the real-time community, but is actually useful beyond that. It replaces the traditional scheduling model, which is based on priorities. The highest priority process is the one that runs right now, with another model that does away with priorities and instead assigns to every process an amount of work that it has to do and a deadline by which that work has to be done. If you are careful about your mission policies, which jobs you actually accept, you can actually guarantee that every process will get its work done by its deadline. This, of course, is very interesting in the real-time world because real-time is all about deadlines. It's also very useful for situations like multimedia processing, where you have this stream of data coming in, and every so often you have to have a certain amount of time to deal with it. And that just goes on and on. So I think we'll see the deadline scheduler put into use in a lot of interesting places as it stabilizes over time. There's still some work to be done in that area. The control group subsystem is sort of the basis of our whole container implementation and many other things. It's a way of grouping processes together and applying policies to them. The charitable way to put this is that the first implementation of control groups that we put into the kernel was perhaps best viewed as a learning experience. We learned a lot about how we should not implement control groups. And so there's been a lot of work underway to re-implement them with a different API and a different underlying implementation that will be much more robust, much more secure, and much more maintainable going forward. This, of course, is a hard job because we can't break the people who are using the current control group implementation. That has to still work. So we have to support them both for the foreseeable future. Much of that work got done over the course of the last year, and we're heading into the new control group world. The multi-queue block layer is a major reworking within the disk I/O subsystem of the kernel. It takes the single request queue, the single queue of I/O requests that we had, and splits it into multiple queues, each one associated with a CPU or a NUMA node. This allows us to keep traffic localized and not move things around the system. That can increase throughput considerably, which of course is something we're always looking to do, and also simplifies a lot of warts that have grown in the block layer since it was first merged in the 2.5 development series, the block layer that we have now. And lots of networking improvements. I can't really list them all, but there is one thing I wanted to call out, which is that our performance with very small packets. It turns out it's pretty easy to drive a high-speed network interface at full speed if you're sending really large packets. But if you're sending really small packets, then the per packet overhead tends to dominate, and performance can go down. And Linux traditionally has not performed as well as we would like in that area, which is a problem because there are important workloads, like, say, high-frequency trading and other things like that, that actually depend on small packet performance. So over the course of 2014, some fairly dedicated developers put a lot of time into this, isolated the bottlenecks and took them out, so we can now actually drive a high speed, like a 40 gigabit network interface at full speed with a single processor with small packets. And that's a major step forward from what we were able to do before in the networking area. So on top of that, of course, we've added hundreds of new drivers, literally hundreds of new drivers. We typically add 50, 60, 70 new hardware drivers in every kernel development cycle. and thousands of fixes to the kernel, and a whole lot of other stuff that I can't possibly mention. So I want to just summarize this section of the talk by saying that this is really kind of business as usual anymore. The development process, as far as I can tell, is running as a very smoothly tuned, well-tuned machine. It just works. We don't seem to be running into a whole lot of process bottlenecks at the moment, which is good. As we've gotten bigger over time, we have had periods where things did not work very well, but it's been a while since we've had one of those. And things are just functioning fairly smoothly. But I can't be optimistic all the time. So I'm going to talk for a little bit about a few challenges that we're having to face at the moment, and then I'll conclude the final part of the talk with some of the cool things that we've done or will be doing in the near future. So first thing that I worry about is the area of testing, and we're not talking about standardized testing, but testing of our kernel to make sure that it works functionally correctly and that it performs well. We've not always had the best story there. We don't have a lot of tests built into the kernel for a lot of reasons, including the fact that, again, most of the problems that come up with the kernel are tied to specific hardware, specific workloads, and kernel developers have access to neither typically. So that's a nice excuse for not having a lot of tests, but perhaps we can do better than that. And the good news is that in a number of ways, we are actually doing better than we were before. We've had the Linux Next tree for several years now. This is where integration testing is done so that when the merge window opens, as it is open right now, and 10,000, 12,000, 13,000 patches all flow into the kernel over the course of just 2 weeks, that they actually mesh well together and play together, and we don't have a lot of conflicts between them. And so we've gotten much better in that regard. More recently is the addition of what's called the zero-day build bot. It's run by Fengguang Wu. He goes out there and he finds development trees all over the net. If you've put out a Git repository with some kernel code in it, he's going to find it, whether you ask him to or not, and pull it into his tree and test it and try to boot a kernel with it. And if something doesn't work, you get this polite little email that says, oh, by the way, you just broke the kernel. And you hate those emails, but actually you like to get them because then you found the problem, you can fix it. I did a quick check and found over 500 fixes in the kernel, all credited to the zero-day build bot over the course of just a couple of years. It's an amazing resource, and it has helped us to find a lot of problems before they ever actually get into the mainline kernel. And there's a ton of static analysis tools out there that are starting to be used to better effect, from proprietary tools like Coverity through to free tools like Trinity and SMatch and Coccinelle and so on. Trinity in particular has been interesting. This is a fuzz testing tool. It just throws random junk at the kernel and sees when the kernel breaks. It's been described as a denial of service attack against kernel developers, because if it gets run against your subsystem, you have to drop everything you do and fix all the bugs that come out as a result of it. So again, we've found, nobody I think has a count of the number of bugs that have been found by Trinity and fixed, and hopefully found before they affect users, before they open a security hole, that sort of thing. So in a lot of ways, our story is getting better. But in other ways, the picture isn't quite so optimistic. I've heard some anecdotal reports that there's a lot less functionality and performance testing going on in the commercial sector than there used to be. Generally, the companies that are charged with shipping and supporting Linux do a lot of this testing, but it seems that they've discovered that everybody else is doing this testing too, and so they think maybe they could do a little bit less of it. And so now there's a bit less of it going on, and that's not necessarily a good thing. There's also kind of a long-standing failure that we've had in that there's no way for a kernel developer to readily check and say, did this change that I just put in break the kernel in some silly basic way? Because every developer will have tests that they run to verify that their particular patch works. But they don't necessarily test to make sure they didn't create some little weirdness in the file system layer somewhere or something like that. The kind of thing that can creep in even in a highly modular kernel. So it would be nice to have some sort of basic sanity tests in the kernel. The good news is that we're actually getting there. There is now a make test target in the kernel that's being worked on. It's rudimentary at the moment, but it's going to get better over time. You're seeing some awfully good work there. And soon we're actually going to have a situation where there should be no excuse for introducing a whole lot of basic failures into the kernel, because we'll have the test set up there to handle it. But the other thing we really need to do is to get back into wider scale testing, because the more people who test the kernel, the better off we are. And this is particularly true, we found, in the area of performance issues. We all want a kernel that performs with power, with strength, and as fast as we can get it. But the problem that we run into here is, imagine you're a mobile systems developer, and you're working on the scheduler to make it more power efficient on small systems like a smartphone, something like that. And so you commit a change. There's really no way for you to know that your change, while it did in fact achieve the desired effect, has just regressed performance on huge database loads on big NUMA systems by 0.5%, right? It's not on your radar, and in any case, if you work on smartphones, you probably don't have a huge NUMA machine handy to test your patches on. And so you won't know this. And in fact, nobody will know this until the change comes out in an enterprise kernel release a couple of years later, mixed in with maybe 20 other patches that have also caused similar 0.5% regressions. And then somebody boots this kernel and their workload runs 10% slower, and they're very unhappy. And by this time, the problem is 2 years old. It's mixed in with literally 100,000 other patches, and it's really very hard to find. So performance regressions are one of the real banes of kernel development at this point. And they're really hard to find. And again, kernel developers can try, but they cannot really find them all because they don't have access to the workloads where these things are expressed. So we really need more people testing kernels as often and as soon as they can so that we can find these things before they become hard to fix later on. In the end, the answer is that kernel testing really is everybody's business. It has been said that this is why we have users in the first place, so that we can get the kernel tested. But you know, that's a little snide. But the point is that the more people who test it, the better off we will be. On a similar topic with regard to everybody's business, let's talk about the real-time patch set for a moment. The real-time patch set has been developed outside of the mainline kernel for quite a few years. A lot of this work has moved into the mainline over years, but quite a bit of it still is outside. It's shipped in various vendors' products and so on. A lot of people use it, but it's not all there. The real-time developers have done a very interesting thing, and they have proved that you can get real-time response out of a general-purpose kernel, something that a lot of people working in this field said was absolutely impossible to do. They have proved it, but unfortunately, they proved something else, which is that you can do this if somebody will support the work. Right? Jim was talking about this morning. This is another one of these areas where the support for the real-time work is pretty much just dried up. And so the developers who were working on that are now working on other things. And real-time is described by the people involved as a hobbyist project now. And so, you know, if anybody is dependent on this work, they should be kind of worried at this point about where the future updates are going to come, how it's going to just keep up with the rest of the kernel as it moves forward. This is something that tends to happen when people think, okay, this is out there, it's a very nice facility, but it's not necessarily my problem to support its development. We have a lot of areas like this, and while things like the Linux Foundation's Critical Infrastructure Initiative are very helpful in this regard, they cannot possibly address all of these areas. It really comes down to the companies that benefit from this work, seeing it as their responsibility to support some more of it. And if we can do that, we'll be in a lot better shape. Okay, related area, of course, is security. And again, this was talked about a bit this morning, so I can skip some of what I was going to talk about because Jim ruined my, my stuff, but not really. But as he mentioned, we had a lot of high-profile security incidents in the last year. This included things like Heartbleed and shell shock, those kinds of vulnerabilities. Also, high-profile compromises at various companies and so on. I get my health insurance from a small company called Anthem, so I'm a little disgruntled by this at the moment. The point is, this kind of stuff is touching a lot of us right now, and as well as revelations of wide-scale surveillance and other things like that going on. There's a whole lot that's going on out there. A lot of people depend on the Linux kernel to be the basis of their security on their systems. I did a quick check in the CVE, the Common Vulnerability Entry Database, and found 115 CVE entries for the kernel in 2014. That's almost certainly an underestimate, by the way, because it takes a while for these things to get in there and associated properly. But even that's way too many. That's a vulnerability about every 3 days in the kernel. A lot of them are minor. Almost none of them are remotely exploitable. but they're vulnerabilities, and they're not a good thing. We do not want that in the kernel, not if we want to be secure. We have problems, of course, with lots of old and unmaintained code. Jim mentioned that the shell shock vulnerability was some 20 years old. The x.org project recently fixed some vulnerabilities in the X server that were 20 years and some old. Really old code tends to harbor some really old bugs that nobody has looked at for a long time. The kernel at the moment has roughly 19 million lines of code in it. I did a quick check and found that a little over 3 million of those lines have not been touched since the kernel went into Git 10 years ago. So we have 3 million lines of code that nobody has done a thing with in 10 years, and probably quite a bit longer than that. So some of that code undoubtedly harbors things that we really wish were not there. It's a problem that a lot of projects we have it too. Of course, there are a lot of motivated attackers out there. A lot of people trying to find these problems. They're often very well funded, have a lot of different motivations. And we have relatively few people working on the problem of actually making the kernel more secure. Way fewer than we have attackers out there. We have a certain number of people working on the fire drill of putting in patches and distributing updates once vulnerabilities are found. But that's not really what we need to do. We need to find and fix these vulnerabilities before they bite people. And I wish we had more people working on it. We could say that things are getting a little bit better. We had 175 CVEs in 2013, but this is kind of a cold comfort. And there is some effort going into the problem. People working on hardening the kernel, trying to find ways of reducing the effects of a compromise or a bug when it does happen, and so on. But it's really not enough. We have millions and millions and millions of systems out there running Linux, incredible numbers of people, billions of people, I think really, depending on the security of the systems of which the Linux kernel is the base. If we're really going to not let those people down, we have to be more serious about the security of the kernel. And I don't really know how we get there because this is not an easy problem. And it's certainly not a problem that is limited to just the kernel. But it's something that we're going to have to work on, I think, for a very long time. Speaking of problems we'll be working on for a long time, the year 2038 is only 23 years away. Time to start worrying. For those who don't know, 2038 is when the 32-bit time t value used on Unix systems since the beginning runs out of bits. And so after January 2038, we simply cannot represent times if that particular time format is in use. And it is in use in a whole lot of places. So a lot of things break. It is our equivalent to the year 2000 problem. And it's a very similar sort of thing. So one might wonder, well, okay, that's fine. That does seem like a problem, but that's 23 years from now. Why do we need to worry about this now? Well, I'll be retired then anyway. And there's a lot of answers, including the fact that perhaps we don't all want to come out of retirement to fix it then. The simple fact of the matter is that systems are being built and deployed now that will still be in service 23 years from now. There are Linux-based systems that are being put into cars, into building control systems, into power plants, and who knows how many other places where they will just simply sit there and do their job until time t runs out of bits, and then they won't work anymore. Those systems are going to be hard to find. They're going to be impossible to update. It would really be better if we didn't spread a lot more of these things out there. We should really fix this problem now. So the good news is that some people are actually working on this problem, and the core timekeeping code in the kernel got fixed over the course of 2014. So in the deepest layers of the kernel, the stuff that actually deals with time is all able to handle this apocalypse now. It's all set for it. The outer layers of the kernel are going to take more work because there's a lot of places where time values show up. For example, the ext3 file system will break. And I don't know if that's ever going to get fixed or if we'll just hope nobody's using ext3 by then. Hopefully not too many people are using it even now. There are various device drivers that use it and so on. So it's going to take a while. But beyond that, there are a lot of system calls, the interface to user space, that use 32-bit time t values, starting with clock get time and going on from there. These all need to be fixed, but of course we can't just change them because if you do that, you break every application that's running that uses them. So we have to come up with a migration path. a way forward where we can transition everybody to year 2038 safe system calls without breaking things in the meantime. And that, of course, can't really be done without cooperation from the developers of the various C libraries that are out there. There have been some conversations that I have seen with the C library developers, so things are being thought about, but I don't know that there's anything resembling a serious plan at this point. There has to be work to be done there. And in terms of actually fixing applications to deal with this problem, well, that isn't happening yet, as far as I can tell. But I would like to put the message out there that if any of you who are working with software out there that deals with time values at all, this problem should be on your radar. Because if we continue to distribute software that has this problem in it, we are setting up problems for the future. And we don't want to do that. The time to fix it is now. So once I am done here, we're going to be talking about the Internet of Things, but I'm going to bring up a subject first. Because people are doing an awful lot of really wild things with the Internet of Things. I mean, very wild things. But one of the interesting aspects of the Internet of Things is that the systems that are being deployed in this area can be quite small. Right? When people think about small and embedded systems, they'll often think about something like a smartphone. This is a little Linux system. But this is a system with the resources that supercomputers had not that long ago. Right? To the people working in this area, a smartphone is not a small system. That's a huge system. We're talking about systems that have, for example, about 2 megabytes of installed memory in them, which is not a whole lot of memory at all. But if you're trying to build a system that you're going to install in your toaster or in a light bulb or in your shoes or wherever you're going to install these things, and you don't want to inflate either the price or the size of it, then you don't have room for a lot of memory, that sort of thing. So 2 megabytes of memory is something that some people are targeting. Compare that to this plot, which was posted at the Kernel Summit last year. This is the size of the smallest kernel you can build, plotted against the kernel release version. So starting with 3.0 and going forward. So we see that, perhaps unsurprisingly, kernels are getting bigger over time. That the amount of memory the kernel takes is growing up to about 1 megabyte of memory for the more recent kernels. So if you're dealing with a 2 megabyte system and the kernel takes half of it, before you even think about running the user space stuff that you actually have the whole system to run, this is a cost that you don't want to pay. And so we have people doing really crazy things like running 2.4 kernels just because it's that much smaller. But that's not the way we want to go forward either. So we have to solve this problem. And it's going to be a hard one because, of course, the growth of the kernel is not going to stop. There are very few kernel developers out there who say, you know what, today I'm going to just make the kernel bigger because I like to see it bloat. Right? The reason the kernel is getting bigger, well, some of those Intel folks are bad, but otherwise, no, seriously, kernel developers don't do this. They add features that people want. They add hardware support that people want, right? So this is going to continue because it is simply what we want. So what's to do? Well, there are people working on this. It's called the kernel tinification effort. You can find their stuff there. And they're doing some really crazy things. They recently posted a patch that totally removes the concept of users and groups from the kernel. So everything just runs as root, there's nothing else. It's just like being way back on an old MS-DOS system. But if all you're running is one single little application on a very highly dedicated system, you don't need that stuff. And so you're not going to use that feature. You might as well take it out and save the memory that is associated with it. They want to remove things like signal handling. They want to do a lot of stuff that will make the kernel look like something very different from your typical Unix-style kernel. And so this, of course, leads to a number of interesting challenges, starting with the question of how do you do this without making a total mess out of the kernel's configuration system? Because if you add 1,000 configuration options for everything you might want to carve out, you're going to create something that's just totally unmanageable and unmaintainable going forward. How do you support somebody who is just, say, remove signal handling from their kernel, and then they come to you and they complain that their application doesn't work anymore? Right? The answer is generally going to be, well, you broke it, you get to keep all the pieces. But these people are going to come forward anyway, and so there's going to be a support issue there. Keeping ahead of the growth, as I mentioned, because the growth of the kernel will not slow down. And developer resistance, because there are a lot of developers who don't really see the point of this work in supporting systems that are so small, and who don't want to have Linux kernels out there that don't look like Linux kernels. And so there really is resistance within the development community whenever a patch like this comes around. And that's going to be a hard one to overcome. I think we're going to be arguing about that one for quite a ways going forward. But I would put forward the simple point that either Linux is going to be suitable for all these applications, or something else is going to come along that will be suitable. And that something else may be a whole lot less friendly, a whole lot less free than what we have in the Linux world. So, we've gotten a little bit smug in the Linux world because, world domination seems to be at hand, even on the desktop maybe. But I kind of worry about the day that somebody puts out this, tiny little halfway broken system for very tiny embedded systems. And people will look at it and they'll say, oh, look at it, it's so cute and it's so furry and it's so fuzzy. But with those short little legs, it can't possibly keep up with us and our thousands of developers and our rate of change and our incredible hardware support and so on. Heck, it's not even housebroken. No one's going to use it. But in typical disruptive system fashion, we may wake up someday, a year or two later, and find out that this cute little thing has grown up and just eaten our dinner off of our table. I do not think that we can just count on the dominance of Linux in this area unless we earn it. And we're going to have to earn it by addressing the needs that these people have. It's a very interesting challenge for us to meet. So enough about that. Let's talk about new and interesting stuff for the few minutes that I have left here. And then we'll move on back to Internet of Things stuff again. So first thing I want to talk about is a concept called sealed files and an associated thing called MFDs. So what's a sealed file? Well, it's not files around seals or anything like that. Instead, a sealed file is a file that has been mapped into memory, populated with some data, and then rendered immutable so that it can no longer be changed. Essentially, you can think of it as read-only memory at this point. Once it's been populated, it's locked up, and nobody can change it anymore. So a MFD expands this concept by doing away with the file, or actually kind of hiding it so you don't actually see it. So you just have a shared memory area that you can seal. And the result is these shareable, unchangeable memory areas. This is a functionality we've had for a few months now. It was merged in the 3.17 kernel. You might ask, well, what's the use of this? And the answer comes down to distributed computing sorts of things, where you have multiple processes communicating with each other over some sort of system bus. If you are exchanging commands and responses over this through shared memory, there's a lot of benefit to knowing that the contents of that shared memory region cannot be changed by the other side. If you send a command to some other process in the system, perhaps a privileged process that's going to do something privileged for you, and then you can twiddle around with the contents of the command while the other process is acting upon it, then you can open up the world to all kinds of bugs, including some pretty serious security type problems, that sort of thing. You can make much more robust systems that you're much more confident in if you know that the contents of that memory cannot change over time. And of course, you can always achieve this by simply copying the buffer, but all those copies cost you as well. You'd rather avoid that. And so that's where sealed files and MFDs come in to accommodate this kind of inter-process communication. And Keith was there waving his laptop at me to tell me he's using it in other contexts as well. But that was what it was developed for. And it was really developed to go with a subsystem that is not yet part of the kernel called KDBus. KDBus is a kernel-based implementation of the dbus inter-process communication scheme. And you might ask, well, why do you want to do this? One of the fundamental rules of kernel development has always been that if a process can be solved well in user space, then the solution should be in user space. The existence of a very successful dbus system that people have used for many years suggests that perhaps the problem can be solved in user space. Well, the answer comes down to a few things, including performance, because if you're writing all of your messages through a user space daemon, you have a lot of context shifts and copying that you can skip if you run it through the kernel. Security, the kernel can provide guarantees to one process about who a message is coming from, what the sender's credentials are, and so on. So you have a much more secure system that way. And early availability, having the system available from the very beginning of the lifetime of the system, rather than having to wait until you can get to where you can actually run user space, so that you can make use of it within the kernel during the bootstrap process and such. So there's a lot of reasons why people want it. It's been posted, I think, 3 times now. The first time was really pretty badly panned for a lot of reasons, having to do with security and support for containers, that sort of thing. The developers listened to the criticism, came back with the second version, which was much better received. The third version, better yet, although there's still some concerns about the API that have been that has been put together for it and so on. So it may yet need to evolve some, but I think it will get there and it will be merged in this year is my guess. And I think that it actually stands out as a real example of how kernel development should work for various reasons, including its support by members of the systemd community and so on. This had the potential to be a very highly contentious, flame-ridden sort of discussion, the sort of thing that makes the kernel sort of infamous. But in fact, none of that has happened. The discussion has been very technical, has been mostly quite friendly, and it has resulted in a submission that is way, way better than what we had the first time it came around. It's just the way the whole process is supposed to work. It's kind of a storybook story. And so if it continues this way through the merger, I'll be very happy with that. All right, something else that's coming up is live kernel patching, because after all, rebooting a system is a pain, and sometimes you simply cannot reboot a particular system, even if there's a really important security patch that needs to go in. So there is value in the ability to apply a patch to a system while it is running, and to keep that system running, and to not even take it down for a few minutes. In fact, there's so much value in it that there's quite a few people working in this area. I did a little looking around and found 5 different implementations of live kernel patching, which is perhaps 4 more than we need. So if you think about which of these implementations might be suitable for merging into the mainline kernel, you can narrow down the list quite a bit. Kernel Care, for example, is a fully proprietary offering as far as I can tell. They've never put their code forward for merging or anything like that. So if it's not free, it's not something that we can merge in the kernel. It's not of interest. Similarly, Ksplice used to be free, but is not free. It's a proprietary offering. It's not something we can put into the mainline kernel. At the bottom of the list, the Parallels live patching mechanism is actually a very interesting solution to the problem, because they're not actually patching the kernel. Instead, they use the checkpoint restart mechanism to checkpoint every process in the system, save its state to disk. Then they use kexec to boot into a totally new kernel that has the fix in it. And then they use the restart mechanism to restart all of those processes running under the new kernel. So the system keeps running. It can happen very fast. But the dependence on checkpoint restart limits it, because checkpoint and restart do not work for all workloads currently. It's a very hard thing to do, to fully save a process to persistent storage and bring it back and have it still be the same process. So for various reasons, it's not something that can be considered an option for everybody. That leaves 2, being Kpatch and Kgraft, which came out of Red Hat and SUSE, both of which want to be able to support live patching for their users. So there's a number of similarities here, right? They both use the ftrace function tracing machinery to intercept calls to functions that have been patched to divert it to a fixed version of it, and so on. But they differ in a lot of other ways, including how they ensure consistency of the system so they can do the patching safely, that sort of thing. There's a lot of differences between the 2 of them. They were implemented pretty much simultaneously using different approaches. So both groups, of course, would like to see their work into the mainline kernel. That was their target from the beginning. But are we going to merge both of them? Well, that's not really how we do things in the kernel. We really want to have one solution that everybody can use that is well tested and well supported. So something's going to have to happen there. The good news is that the developers involved have gotten together and agreed on how to implement a common base layer that they can both implement their live patching systems on. So the first parts of this base layer have in fact been merged for the 3.20 or 4.0 kernel, which will be released in a couple of months. So there have been reports out there that we have live kernel patching now. We're not quite there yet. There's a fair amount of work to do, even with the common layer that's in the kernel, much less building the sort of distributor-specific ecosystem on top of that. So we don't have it yet. And to say that we truly have it is to overstate things. But we're getting there, and by the end of this year, I think we will. And we'll have a feature that a lot of people have been wanting for quite some time now. And then the last sort of cool feature that I want to talk about is virtual machines in the kernel. And when I'm talking about virtual machines here, I'm not talking virtualization like Xen or KVM or something like that. I'm talking about an abstract machine that has its own language where you can actually load a program into the kernel and run that program within the kernel's environment to do things that the kernel was not previously programmed to do. And so you think about that and you might say, well, why on earth would you do something like that? That's not the kind of thing we would ever want to have in the kernel, right? Well, I did a quick look and I found 5 of them in the kernel now. The ACPI subsystem has the interpreter for the AML language that's not only running a virtual machine in the kernel, but it's running programs written by BIOS authors. So you should be very afraid of this one. NetFilter and ftables are both using virtual machines to decide which packets can pass through a system's firewall and which ones cannot, and perhaps what kind of processing should be done. The tracing subsystem allows filters to be attached to trace points, deciding when a trace point should fire or not, and there's a virtual machine that implements that. And then the one I want to talk about is a thing called BPF, which is used with socket filters now, making decisions on which packets are allowed to go through to a socket, which ones will not be. BPF started its life as the Berkeley packet filter, I think in the 1980s, honestly. If it wasn't the 80s, it was shortly thereafter. It's been around for quite a while, used with tools like TCP dump and things like that we used to run on our Sun systems. And the idea is used to run a little program on every packet that comes into the system or into the tool and decide whether it's an interesting packet or not. It has since then in the Linux kernel been purposed to be used with the secure computing subsystem, where it can actually make decisions on which system calls sandbox process is allowed to make and which ones it cannot. So it's been used in this form for a while now. What I'm going to talk about is a thing called extended BPF, or eBPF. This is a development effort that has come to fruition pretty much over the course of 2014. A lot of code went into the kernel to extend the BPF language and make it much more powerful. So it's added a whole bunch of registers. The original virtual machine had exactly 2 registers, which limits things quite a bit. A whole bunch of new instructions, which are very suspiciously like x86-64 instructions in their makeup and their functionality. That's there to allow just-in-time compilers to actually compile a BPF program down to machine language and get the interpreter out of the system entirely. There's the ability to call functions within the kernel. These are functions that are made available explicitly to a BPF program. You can't call arbitrary kernel functions from a BPF program, but you can call functions that have been exported to it. There's a program verifier that will inspect any program before it is put into the system with one of those new system calls I mentioned, which the BPF system call, and verify that the program is safe for the kernel to run. So it verifies the program doesn't address memory that's not supposed to, that it has no loops in it, so it cannot bog down the system, things like that. If it does its job, then any program that the kernel accepts is safe for the kernel to run. And there's a concept called maps, which are a sort of associative array allowing sharing of data between a BPF program and either the kernel or user space. So that's how the communication happens between them. So they've had a lot of functionality there and moved it out of the networking stack where it lived for quite a while and into the core kernel. So it's available for any part of the kernel to use. And we're going to see it used in a lot of places. It'll move into the secure computing subsystem. I've seen patches going by to move the tracing filters over to this mechanism and perhaps someday do away with the separate virtual machine that's used there. Some people have talked about replacing the nftables virtual machine, although that will take quite a bit longer to happen, if it happens at all, because that machine was developed with different goals and has some different functionality in there. And I've seen patches adding BPF functionality to other parts of the kernel that I hadn't really imagined into the Open vSwitch stuff, I think, and various other things. So it's going to pop up in a lot of places. It's really become the standard virtual machine for kernel functionality. And I think we're going to see people doing some very interesting things with it. Just to conclude, as I'd say that this is it's an interesting functionality. One might regard it as a fairly crazy expansion of the user interface supplied or offered by the kernel. And like many aspects of new interfaces, it's got a problem, which is that people actually use it. You know, if people didn't use the stuff that we did, we'd have a lot less trouble, but they do use it. And this brings a lot of associated issues, meaning that once people become dependent on a kernel feature, we have to support it forever. We cannot take it out, we cannot break it, we cannot change it in ways that break programs out there. We have a very strong rule about that. If you submit a patch that breaks things, you can expect to get a very precisely worded message from Linus on just how you don't do that. And the problem is that we're not always very good at designing these APIs. The control group example is one that comes to mind where it's just generally regarded that we just did it wrong. And there are various other examples out there. There's 4 versions of the wait system call now. This is a problem that actually predates Linux in a way, but it has continued since then because we keep thinking of things that we didn't think of before. So we have to keep doing this sort of thing. And this brings about all kinds of maintenance issues as you go forward because we cannot break things. So we have to carry the old version and the new version. And so this is perhaps the biggest challenge that we're going to face as we go forward in time, is that how can we blaze new trails in the kernel? Because this is what we're doing. We're way, way past the day when we were just making a better Unix kernel. Right? We're bringing the kernel into areas where systems have not been before. We're adding functionality that people have not really defined over years and standards committees and so on. So we're doing new stuff, and we don't really have a map to guide us. How can we do this without making a mess of the kernel that we have? We've actually managed it over the course of 20-some years so far. I assume that we'll manage it over the course of the next 20-some years as well. But it's going to be very interesting to watch and very interesting to be a part of. And on that, I'm pretty much out of time. Time to move on. So I will thank you all very much for your attention, and